Okay, problem 8.7. So it says that there's a sufficient condition for the central limit theorem we learned in class. If x1s or xn are independent and uniformly bounded, meaning that they're all bounded in a certain interval, their values can only be from a fixed interval. And if the variance of their sum goes to infinity, so the variance of this y, which is sum from x1 to xn, becomes infinity. So let n go into infinity, let all go to infinity, let n tend to infinity, and the variance of y tend to infinity as well. Then the standardized mean of xi, that means the sample, if this is the sample variance, sample mean, this guy, right? Sorry, it's a little n xi, so that's the sample mean. Standardized the sample mean means that this minus mu. Mu is the mean of the of the original distribution and divided by sigma over square root of n. So that is the standardized mean, right? We know that, but central limit theorem says that this will be more and more like the standard normal random variable. So then here it says that this will go to standard normal, or distribution of this guy. The distribution of this guy is approximately the standard normal distribution, given that condition right here, which is this goes to infinity. So the question is, can we show that this condition indeed holds for this particular type of distribution, where, remember here that these xi's could have different distributions. They're independent, but they could have different distributions. And right now, here it tells you that each guy has this distribution. So for the ith one of this random variables, the ith one has the probability equal to 1/2 when the xi is equal to this value, and they equal to 1/2 again when the xi takes this value. So basically what that means is, if you're trying to plot the PMF of xi, then you will see that here this is a 1, this is -1. So this point here is this 1 minus half to the I. Okay, and here this is actually symmetric to the point on the right. This guy here is the 1/2 to the I minus 1. So you can only take a value of 1/2 here. So this is the 1/2. So take a value here and here. So that is so these two dots actually give you the PMF for the random variable xi. Okay, and it's actually symmetric about the the vertical axis. So now if you want to show that the variance of this y goes to infinity, as n goes to infinity, we need to know the variance of each of these guys, because they all have the different distributions. We need to know the variance for each of them. So to calculate the variance, we're going to calculate the mean first, and then calculate the second moment. So the mean, which is the first moment, and then variance, which is the second moment. So following the definition, the mean is just equal to a weighted average of the possible values using the probabilities as a weight. So basically the weighted average of these two values using these two as their weights. So they'll basically have the value of this guy times 1/2 plus the value at this point times 1/2. And you can see because they're just negative of each other, so you add them up, you just get 0. So the mean is actually 0 for xi, for every xi. And the variance, or the second moment for xi, by definition, just xi squared all times fi of xi. So remember that here, this is just the weighted average of those xi squares, where xi are the possible values the random variable xi can take, and this is just the weights for that for those average. So again, this is just 1/2 for those 2 points, and then the 2 points are this, right? This point and this point, but remember, you need to square them. So, so this square times 1/2 plus this square times 1/2. So you can see that these two guys are the same after square. They are the same, and you have the 1/2. So you essentially add them up. So that is actually the second moment. The variance is just the second moment minus the square of the first moment, but this guy is just 0. So as we showed, it's just 0 here. That's why we'll just have this as the variance. Now we have this as the variance, then the variance of the y is essentially just the sum of the variance of xi's because xi's are independent. And then we just simply need to sum up those things. Right? We need to sum up this. Excuse me. Now you have this term. We need to show that it goes to infinity as n goes to infinity. So it's pretty, it's a little bit tricky here, but you can realize that this one here, this inside here is always a number bigger than or equal to 1/2, right? Because it's a 1 minus 1/2 to the power I. The I is 1 or 2 or 3, some number like those. So this is just a 1/2 or 1/4 or 1/8, something like those. So the 1 minus this guy will be bigger, will be a number like 1/2 or 3/4 or 7/8, something like those. So they're all bigger than or equal to 1/2. So you square them, they're all bigger than or equal to 1/2 squared. And so each term is bigger than or equal to 1/4. And you take the sum of n of those terms, so they should be equal to bigger than or equal to n over 4. But you know that the n over 4 will go to infinity as n goes to infinity. So that's why the variance of y indeed goes to infinity as n goes to infinity. So that verifies the condition, right? We actually show that this becomes infinity as n goes to infinity. So that this proves the sufficient condition actually holds.